Till now we have seen the the scheduling algorithms with the processes where burst time is given, and by burst time they mean to say only CPU time. And now we shall see the examples where burst time will include one is CPU time as well as IO time. So a process can spend some time in the at CPU, and then it can spend some time in the IO devices also. If that is the case, watch it. So a process can have three types of times, two types of times. One is burst time, during which it requires the CPU to finish, and other is IO time, during which it requires IO devices. Therefore from CPU it will get out to the IO devices and it will spend some time there, and again it will come back, right? And then finally burst time. Now we want to schedule these processes in such a way that, see this, and one more thing, this order has to be in the same way, which means a process will be in the CPU for 3 units, and then IO for 2 units, and then CPU for 2 units, right? And the algorithm we are following is shortest remaining time first. So what is the shortest remaining time first? We are going to see the one which is having the least burst time and schedule it first, and later if any process arrives with least burst time, we will schedule it by preempting the first one, the earlier one, right, the present one. Now in this you need not count IO burst time at all. Without counting it, you can count these two as burst times, right? Therefore the burst time of process P1 is 5, process P2 is 3, and process P3 is 3, and process P4 is 3, right? That is the burst times, 5, 3, 3, 3, right? And now which one is the least one? So let's draw the Gantt chart and you will understand it. Okay, with this example you will understand it. Instead of explaining it before, I'll just take the example and make it clear. Now at time t equal to 0, what are the processes that arrived? P1 and P2, these are the two processes which arrived at time t equal to 0, right? At this time we are going to schedule anything, but then we are going to pick the one with the least burst time, right? So P2 is the one with the least burst time out of these two. It is having 5 and it is having 3. See, it is having a burst time of 5 and it is having a burst time of 3. It is having a burst time of 3 and it is having a burst time of 3. Only CPU burst times, right? Fine. Therefore let me schedule P2 first. Yes, P2 is scheduled, right? And how long should it run? Until I get any other process which is having a lower burst time, right? But then even if you run it till 2 units, if I run it till 2 units, right? Even if I run it for 1 unit, let's say you didn't run it for 2 units, you had run it for 1 unit. Even if you run it for 1 unit, then also what happens is the processing time, the burst time requirement of this process will fall to 2, and by that time the next process, no process is available. Therefore nothing changes. So I could even go ahead and run it till 2, and at this time one more process got available and its total requirement is 3, and we have already finished 2 times and it requires only 1 more unit, right? But the problem is you cannot run it further, you cannot run this 1 unit unless you finish the 4 units of this CPU, that IO. Therefore at this point process P2 will go for IO. Which one? Process P2, right? So how long will it go for IO? For 4 units. Therefore for 4 units you should not consider P2 for scheduling again. It is simple like this. Initially it is in ready queue, and then it went to the running, and from running, instead of coming back to ready, it is now in block state, right, waiting for the IO. So how long will it be there? For 4 units. Therefore for this 4 units you should not pick it for running because it is not present in the ready. Now time is 2. Now by this time 2, let's see what are the processes which are available. P1 is available and P3 is available, right? And out of these two, which one is having least burst time? P3 is having least burst time. Therefore you could schedule P2, P3, isn't it? Now I am scheduling P3, and it is saying that it can run for 1 unit and then it has to go for IO. Therefore at this point I'll run it for 1 unit, and again at this point it is going for IO. Which one? P3 is going for IO, right? How long will it go for IO? If you watch it, the time required by P3 for IO is 3 units, right? Now from 2 it requires 4 units, and from 1 it requires 3 units. Therefore 2 plus 4 is 6, and 1 plus 3 is uh, 4, right? Let's see that later. But then anyway, right now this P2 and P3 both are in block state, where when time equal to 3, both P2 and P3 are in block state, isn't it? And now what is the next process that we have to schedule? So time equal to 3, now nothing is available, only 1, 2, 3 are available, out of which 2 and 3 are already, they are at now in the block state. So only process which is available is P1. Out of no choice, I am going to schedule P1 now. I have only one remaining choice, P1, and I have no other choice. I have to run it till the next one is available, right? So I'll run it till the next one is available, which is nothing but 5, right? And now after running it till 5, then the next process 5 is available, right? Okay, at this point just analyze it, what has happened. Now at this point 5, I have run it for 2 units, which means its requirement is 3, and a new process has arrived whose requirement is also 3, right? Therefore both the requirements of the process are 3. You could go ahead and run it for one more unit. So I am running P1 for one more unit, which means till 6. So P1 has now run for totally 3 units. 3 to 6 is 3 units, and at this point P1 has to go for IO. So let's see what has happened to P2. See, P2 has gone for IO at time t equal to 2, and now time t equal to 6 has happened. So at this point the P2 has finished its IO, and similarly P3 has gone for IO at time t equal to 3, and now it has taken 3 units, which means at time t equal to 6 even P3 is also done with its IO. But then if you look at P1 has just gone for IO, and it will require 2 more units, isn't it? So now P1 is not available, but suddenly P2 and P3 are available. P2 is available, P3 is available, and then P4 is also available, because time is now 6 o'clock, 6 units, right? And then P1 is only the one which is in the blocking state. So you don't consider P1, and you just see what are the remaining ones, and among them which one to schedule. Just watch it. P2 has already finished 2 units, right? So P2 has already finished 2 units, it requires only 1 unit. And P3 has finished how many? 1 unit. Therefore P3 finished 1 unit, and it requires 2 units more. And then P5 has not finished anything, it requires 3 units more, right? So among P3, P4 and P2, P3 and P4, they are in the ready queue. Which one are you going to schedule next? Obviously the choice is P2, because it is having the shortest remaining time. So I'm going to schedule P2 here, and it will run for only 1 unit, which means till 7, and it will be over, right? Therefore P2 is over at this point. Fine. And now P2 is not there in the ready queue, it is over, it has gone to the termination. And now I have P3 and P4. What happened to P1 here? See this, how long does P1 want to do the IO? It wants to do it for 2 units, right? Which means if it started at 6, it will not be over till 8. So P1 is not yet available. Now I have to make a choice between P3 and P4. Just watch it. P3 and P4, which one is having lower burst time? 2, P3. Therefore I am going to schedule P3 until what time? Until the next process becomes available, right? So what is the next process that becomes available? At this point, if I run till 8, right, at this point P1 will also become available. Why? P1 has gone for IO only for 2 units, and it started at 6. By 8 it must be available in the ready queue. Therefore now P1 is available, and now we have run this P3 for 1 unit. Therefore remaining time for P3 is 1. And now the total number of total process available is P1, P3 and P4. Now among P1, P3 and P4, the requirements are like this. P1 requires 3 units, isn't it? Why? Because P1 has run only for 2 units, 3 units. I think P1 requires only 2 units, right? See this, here P1 has run for 2 units and then 1 more unit. Therefore P1 requires only 2 units. Fine. Now watch it. Among this P1, P3 and P4, P1, P3 and P4, right? Which one is having the lower time? P1, P3 and P4, it is P3. Therefore you have to again schedule P3 itself, which means P3 will keep running for 1 more unit, which is 9, right? And at this point P1 is over, right? P1 completed. Then what are the two processes remaining? One process remaining is P1 and other process remaining is P4. And among these two processes, which one do you want to schedule? P1 requires only 2 units, therefore P1 is obviously the candidate. Now P1 will be scheduled for how much? 2 units of time. Therefore it is going to run till 11 and it is going to be completed. And finally we are going to schedule the P4. Till now P4 never got scheduled, right? So finally P4 will get the chance to run, therefore P4 can run completely. And how can it run is, see this, P4 is scheduled at what time? P4 needs 2 units of time, burst time, therefore till 13 it can run, and after that in what happens is it will go for IO, therefore there is no process currently to run. For the next 2 units there is no process to run, which means this complete 2 units of time, 13 to 15, CPU is completely idle because all the processes are over, only one process is remaining, which is nothing but this P4, and P4 is also going for IO, therefore CPU has no process to run, so it is going to be idle at this point. And finally it requires 1 unit of time, therefore I am going to run it and finish it at 16. Okay, observe this, it is somewhat difficult to understand. Such a question has never been asked in GATE and I don't know if they are going to ask it. But anyway, if you didn't understand it, you could leave it, but then it is better that you know it. Maybe you could, if you watch it for 2-3 times, you'll understand it. See, I'm not doing anything simple. I'm just using the parameters, and then it is ordinary, like just like shortest remaining time first, but I have to keep track of when is a process going for IO and when is it going to come back. Therefore you have to move the process between block state and the ready state and the running state. Earlier it was just moving them between the ready state and running state, it was easy, but now we have to keep track of 3 states. That is why it might look difficult. So maybe, okay, I'll solve more examples. With that you will be able to understand it, but then you practice this until you can't get it wrong. Okay, you practice it 3-4 times, it must be easy. Watch it 3-4 times and then practice it 3-4 times, it will be easy. Okay. So finally P4 got over at 16, right? So interesting questions about it will be, what are the what can I say, completion times. So asking about turnaround time and then waiting time is going to be a bit tricky and somewhat difficult. So let's talk only about the completion time. So already we have done a complex computation here. So let's talk about completion time. What is the completion time for P1? P1 got completed at 11. And what about P2? P2 got completed at 7. And P3 got completed at 9. And P4 got completed at 16. These are the completion times, right? And if you are looking at how to find out the turnaround time, okay, turnaround time is fine, completion time minus arrival time. So turnaround time for the first one is 11, for the second one is 7, for the third one is 7, and for this one is I think 11, right? Turnaround time is fine. Then what about the waiting time? It is tricky. In the sense, waiting time previously was turnaround time minus burst time, right? But now the burst time is a combination of 2 burst times, not just a single burst time. So how to find out the waiting time is, you have to take from 11 a sum of these 2 burst times, which means 11 minus 5. Are you understanding it? This is burst time and this is burst time. Therefore you have to decrease you have to reduce these two from this 11. Then 11 minus 5 is 6. And 7 minus 3 is 4, and 7 minus 3 is 4, and 11 minus 3 is 7, 8, right? So if you are understanding this, I am not going to include this one in the computation of in the subtraction, because this time is also actually waiting time. So therefore this one has also reflect there. That is why I am just deleting. If you are observing it, that's why I was just trying to delete only the time spent at the CPU, and everything else is waiting time. Either it is waiting for IO or it is waiting in the ready queue. Everything is combinedly called as waiting time, right? And you can find out average turnaround time and average waiting time. It is a bit difficult question. I don't think that they'll ask it, but still it is better that you know it. Fine.